Hello and welcome back to Total Organic Chemistry. This video we're going to be taking a look at stereoisomerism, just an introduction to stereoisomers, and about what kinds of molecules have those types of properties. So, as I've talked about in previous videos, a stereoisomer is a molecule that has the same, or two sets of molecules that have the same connectivity. So all of their atoms are connected in the same way, but they have a different arrangement in three-dimensional space. So this is separate from things like constitutional isomers or conformational isomers. And if you'd like a quick review on any of those other types of isomerism, please be sure to subscribe to my channel and take a look at some of those previous videos where I've discussed those topics. So 3D space. And one of the easiest types of stereoisomers to understand are called enantiomers. So enantiomers are compounds that are non-superimposable mirror images of each other. So non-superimposable mirror images. So let's break that down. Imagine you have two human hands. So we can maybe draw that like this. Not a great artist. Draw maybe one hand like that, and the other hand is just the opposite. So we'll have two hands here, maybe your left and right hands, and these are mirror images of each other, right? So ignore my bad drawing and imagine that these hands are exact mirror images of each other. But imagine both of these hands are kind of pointed outwards towards us. If I draw sort of the palm here. And you cannot superimpose your hands on each other. So you can place them together, facing each other, if you want to try that right now. But you can't place your hands one on top of the other facing the same direction, because then your fingers will not match up. So you have your thumbs, one on each side. So they're non-superimposable, but they're the same. They have the exact same connectivity. You have a palm, a thumb, and four fingers. And they're each connected in the same way, but different orientations in three-dimensional space. So your hands are enantiomers. If we look at something in the chemistry world, so maybe we have a molecule, a substituted methane here. Let's maybe have hydrogen going up, bromine, and we'll have a wedged chlorine. So remember, wedged is coming out at us, towards us, and fluorine with a hashed bond going back into the paper. And what if we draw maybe a mirror plane right here? So let's flip this over the mirror plane. And we have fluorine, again chlorine, and bromine over here in the plane of the paper. So again, these are mirror images of each other, but they are non-superimposable again. There's no way that you can rotate and move around this molecule on the right in order to make it look like and to be superimposable with the atom, or excuse me, the molecule on the left. So because these are mirror images and they are non-superimposable, they are enantiomers, so they are different molecules. We could also maybe try drawing another type of substituted methane. So what about dichloromethane, which is a really common solvent? And our mirror plane here, and then maybe flip everything over the mirror plane. Have our two chlorine atoms here. So these are also mirror images, right? We've flipped everything over. But what you can do is you can just rotate this molecule around that axis, and it'll look exactly like the one on the left. So these are not enantiomers because they're mirror images, but they are superimposable. You can rotate one in order to lay it directly on top of the other molecule. So these are the same compound. And if any of this visualization is very tricky for you, I know it definitely was for me when I started learning organic chemistry. It's one of the hardest things to visualize 3D orientations of molecules. Then consider getting your hands on some sort of stereochemistry set or a molecular modeling set. Usually you can find those for pretty cheap, and they really help with understanding stereochemistry especially. You can really build the molecules in 3D space and hold it in your hands and really see how these enantiomers work. So another word we have for these stereoisomers or enantiomers is that they're chiral molecules. So these are chiral. Your hands are considered chiral. And these compounds would be achiral. So this dichloromethane is achiral because it doesn't have an enantiomer. Its mirror image is the same compound as itself. Another example of a chiral molecule is called Carvone. And if we draw this here, then we have a methyl group. We have this, oops. Have a ketone. And these are all functional groups we will learn about later in the course. And then here's the interesting part. So here's one enantiomer of Carvone. And then what if we have our mirror plane again? So we just flip everything over the mirror, and we draw the exact same thing. So we have our hydrogen going into the plane, and our other substituent going out of the plane towards us. So these are enantiomers, right? Because we have a mirror plane. These are mirror image compounds. But if you try to rotate or transform this molecule here, you're never going to be able to get it to match up exactly or to superimpose with the molecule on the left. And what's very interesting about these molecules, so this is called Carvone, is that this enantiomer of Carvone smells like caraway seeds, whereas this enantiomer has the odor of spearmint. So although they smell similar, your nose can actually differentiate between these two enantiomers. One smells one way, like caraway, and the other enantiomer smells like spearmint. And that's because the sensors, the receptors in your nose, are actually chiral themselves. And that is one important property of chiral molecules, which we'll talk about in a second. So one thing to note is that chiral molecules are so they don't have a plane of symmetry. Do not possess a plane of symmetry. So for example, for Carvone here, we can't find any plane of symmetry through this molecule. There's nothing really symmetrical about it. And also they have carbons with 4 different substituents. So that's something to look for whenever you're trying to determine if a molecule is chiral. Oops. Is to look at all the carbon atoms and see if there are any with 4 unique substituents. So for example, if we look back at Carvone here, which of our carbon atoms has 4 substituents that are distinct? Well, this one right here. So we have 1 substituent, which is the hydrogen. 1 is this group here. 1 substituent is this side of the ring, and the other substituent is this side of the ring. And because the ring is asymmetrical, if you go clockwise this way or counterclockwise, you will get different connectivity, different atoms, so we consider those to be different substituents. And that makes this carbon a chiral center, or a stereocenter. So we can say that these make up stereocenters. So one last thing I want to talk about is the properties of enantiomers. So enantiomers have the exact same physical and chemical properties. Which is very important for chemistry, and especially if you're doing the chemistry in a laboratory or a factory or something like that. You want to be aware of this if you're ever working with enantiomers or chiral molecules. So if you have a set of enantiomers, so those compounds will be of the same melting point, the same boiling point. They will participate in the same chemical reactions, save for a couple that we'll discuss in a second. And same densities, same appearances. They will be almost exactly the same in every respect. We have a couple exceptions. The first of those is how they treat light, how they interact with light. So one property of enantiomers that you will often come across is that they rotate plane-polarized light. And each enantiomer will rotate that light differently. So what does plane-polarized light even mean? So if you turn on a light bulb or shine a flashlight, you're going to end up with light where all of those electromagnetic waves are pointing in every direction. So remember, light is an electromagnetic wave, and that electromagnetic wave is pointing in a certain direction. And in a regular light bulb or flashlight, like I said, those waves will all be pointing in every which way. They won't have any defined direction. But if you pass that light through what we call a polarizer, then you will get only one direction of light out. So let's say all these waves are now just pointing straight up and down. And that's important for us because now, if we pass that plane polarized light So this is plane polarized light. If we pass that plane polarized light through a sample of enantiomers, so say we have enantiomers or chiral molecules in here, what we get out is that light will be rotated. So let's say now it's pointing this way. And then what we can do is we can measure that change. We can measure how much the light was rotated by with a polarimeter. So that tells us how many degrees or how far was that light rotated. And I won't go into too much detail about the mathematics or the physics of this, but what's important to know is that polarimeters can tell us how much of a certain enantiomer we have. So they can tell us the ratio of enantiomers in a certain mixture. So if we have a sample with 100% of one enantiomer, so we call that enantiomerically pure sample, then it's going to rotate that plane polarized light as much as it can, given a couple of values that we can just plug into certain equations. But if we steadily add in the other enantiomer, then that light will rotate less and less until we reach a ratio of 50-50. So 50-50 mixtures of enantiomers will not rotate plane polarized light. And that's important because one enantiomer will rotate light in one direction, say clockwise for example, and the other enantiomer will rotate light the same amount, but in the other direction, maybe counterclockwise. So if you have 50% of each enantiomer, you will not get any net rotation of that light. So like I said, I'm not going to go into too much detail about how this really happens, but it's important to know, and it's important to understand how we measure the ratio of enantiomers in certain mixtures. Another thing is that chiral molecules, I'll make a 2 here, chiral molecules react preferentially with other chiral molecules. So if you have two chiral molecules that are different, so we're not talking about just enantiomers anymore, but we have one chiral molecule and then a completely different molecule that also happens to be chiral, those may or may not react preferentially with each other. And that has important ramifications in the realm of biochemistry, where we talk about enzymes a lot. So a lot of times enzymes are chiral, and they are built to catalyze or to make certain reactions happen over others. And because a lot of biochemistry is chiral, so a lot of the molecules such as amino acids, proteins that we have in our bodies are indeed chiral molecules, then the chirality of those enzymes will allow those reactions to occur much more quickly. So those enzymes will react preferentially with one enantiomer over another, which has, like I said, very important ramifications for our natural body chemistry. So that concludes my introductory video to stereochemistry and enantiomers. As always, thank you again for watching Total Organic Chemistry, and please be sure to like and subscribe to my channel. And also, please consider donating to my Patreon page, which I will link in the description. Like I always say, it really helps me continue to make content for you and provide you with more material.